Hey folks, my name is Nathan Johnston. Welcome to Lecture 20 of Vector Calculus, which is our first lecture about path independence of vector line integrals. Okay, so the setup today is think back to the things that you know about vector line integrals already. Okay, remember that a vector line integral, it doesn't care about the parameterization or path that you're using. It only cares about the underlying curve that's being traced out and the orientation of the curve, right? If you have a curve going from point A to point B, well, the vector line integral that way is going to be the negative of the vector line integral going from point B to point A. Okay, if you flip the orientation, you introduce a negative sign into your vector line integral. But other than that, the parameterization doesn't matter. Okay, it doesn't matter how fast the path traces out the curve. It can go fast and slow, or slow the whole time, or whatever. You're going to get the same value for your vector line integral. Okay, well, the additional thing that we're going to tack on today is it turns out for lots of vector fields, it doesn't even matter what the curve is. All that matters is where you start and where you end. You can trace out a curve, going one way from point A to point B, and then you can trace out a completely different curve going from point A to point B. And for lots of vector fields, you'll get the exact same vector line integral. Not all vector fields, but for lots of them. So what we're going to start doing today is we're going to play around with some examples and try to get some intuition for why this happens at least sometimes. And then we're going to have, quite a few more lectures on this topic, and we'll start introducing theorems that tell us exactly when this happens and so on. Okay. But for today, let's just get started with some examples. Okay. So let's start off with this one here where we've got a vector field, acting on two-dimensional space given in this way. Okay. The vector field is xy squared and then x squared y. And what I'm going to do is I'm going to compute two vector line integrals over this vector field, both going from, 0, 0 to 1, 1. Okay, they've got to go between the same points for this path independent stuff that I'm talking about to be relevant. You do need the same endpoint still. But yeah, like what we're going to do is we're going to compute this vector line integral once with the straight line segment from 0, 0 to 1, 1. And then once again with a different curve, this time a portion of the parabola y equals x squared, but going between the same points, going from 0, 0 to 1, 1. And we'll see that, yeah, these two vector line integrals, they're actually going to be exactly the same as each other, okay? And that's what I'm talking about when I refer to path independence of line integrals. Sometimes it doesn't even matter if you integrate along different curves, as long as the endpoints are the same, you're going to get the same vector line integral. Okay, and let's see that that happens in this particular case at least. Okay, so let's just compute these by brute force using the formulas that we already know for vector line integrals. Okay, so for this first one, you need a parameterization. Well, it's this straight line segment here. It's just, well, t for t going between 0 and 1. Okay, in general, right, if you want to parameterize y equals f of x, you just say x is t and y is, f of t. Okay. Anyway, all right, so there's the parameterization of that straight line segment. So this vector line integral, it's f of the path, f of what I'm calling x1 here. So I'm just plugging t in for x and t in for y, right? T in for x, t in for y, and I get t cubed, and you dot it with the velocity vector, right? This path, take the derivative of each entry, it becomes 1, 1. You dot those together, you're going to get 2t cubed. You integrate that over the range of t. Well, the range of t is from 0 to 1. And you're just going to get a half, right? Because the t cubed becomes a t to the power 4, and then the constant in front is 2/4, which, well, you end up getting a half. All right, so the vector line integral along this first curve here, yeah, it's a half. What about along the second curve? What about along that curve C2? Well, this is sort of a parabolic arc here, but going between the same points. What's our parameterization of that path? Well, x is t, y is just, x squared, which now is t squared, okay? And again, t is going from 0 to 1. Then our vector line integral along that curve, it's going to be, well, integral over the range of t, or sorry, the domain of t, so from 0 to 1. And then let's see, f of x2. So what I'm doing is I'm plugging x equals t, y equals t squared into my vector field, which is up here. So all the x's become t's, all the y's become t squareds, and when I do that, I end up getting t to the power 5, t to the power 4, and again, dot it with your velocity vector, because that's how you compute vector line integrals. So 1, 2t. You take the derivative in each entry, and you get this. You dot that together, you're going to get 3t to the power 5, and you integrate that, you're going to get 3t to the power 6 divided by 6. You plug in your endpoints, oh, you get a half. You get the exact same value for your vector line integral. Okay, so that's kind of suggestive. That's hardly a proof because this is just two particular paths between two particular points, but this is kind of suggestive of what I'm talking about. Okay, if you have the same endpoints but different curves going between them, and your vector line integrals are always the same, that's a vector field that we say has a path independent vector line integrals. Okay, so that's what we're talking about in this video. Definition time. Okay, so path independence, what's it mean? Suppose that you've got a continuous vector field acting on, some domain. Okay, some n-dimensional domain. We say that that vector field has path independent line integrals if the vector line integral along one curve is equal to the vector line integral along another curve whenever you have two simple piecewise C1 curves in that domain that have the same initial and terminal points, okay? The same start and end points, in other words. Okay, in other words, just what path independence should mean based on the words there. Okay, it just means it doesn't matter how you get from point A to point B. All that matters is that you do get from point A to point B. Okay, well, then your vector line integral is the same. All right, so in other words, if we draw sort of a toy picture here to illustrate what we're talking about, in other words, for these types of vector fields, all that matters is where you start and where you end, okay? It doesn't matter which route you take to get there. You can follow this sort of, I don't know, almost piece of a circle here, or you can follow a ridiculously complicated curvy thing. Doesn't matter. As long as you start at A and end at B, you're going to get the same value for the vector line integral either way. Okay. And as you can probably guess, this is extraordinarily useful computationally. When this is the case, this is super duper useful because if you want to compute, if this was the thing you actually cared about, I want to compute how much work is done by the vector field as I follow this path. Well, I could compute this vector line integral instead, and it's probably going to be a lot easier, right? Just pick a simpler path, maybe even a straight line segment path going between the 2 points, and you're going to get the same answer if your vector field has this property. Okay, so it's going to be some work trying to figure out which vector fields have this property. We'll get there when we get there. Okay, let's walk before we can run. Let's start off with an example just to convince you that no, not every vector field has this property. There are lots of vector fields out there that do not have path-independent line integrals, like this one here, y negative x. How do I convince you that this vector field does not have path-independent line integrals? Okay, and maybe to start, I'm just going to show you what this vector field looks like. If we plot it, here's what it looks like. You can imagine the flow lines are just circles, the particle in this vector field is just flowing clockwise around the origin or something like that if I was to drop a particle on this vector field. Okay, and to convince you that vector line integrals, they're not path independent here, imagine that you had some path going from 0, 0 to 1, 1. And suppose that that path followed very closely to the x-axis and then went more or less straight up to the point 1, 1 from there. Okay, that vector line integral, I would expect its value to be very negative, right? Because as it's moving to the right along the x-axis, its direction of motion is perpendicular to the vector field. So there's no contribution, right? You get a vector line integral when you go to the right of 0. And then when you go up, okay, now you're going to get a negative contribution to your vector line integral because you're going away from the vector field. Okay, whereas if I followed a different path, if I followed the path that went up the y-axis and then over, well, this time I expect a positive vector line integral, right? Because again, when I go up the y-axis, well, that's perpendicular to the vector field, so I expect 0 contribution there. But then when I move to the right, well, now I'm moving with the vector field, so I expect a positive contribution there. That vector line integral is going to be positive. So depending on how I go from 0, 0 to 1, 1, I might get a negative line integral or a positive line integral. I'm not going to get the same value. Okay, let's pin this down into an actually precise calculation here, but using these sorts of ideas. Okay, I'm going to pick 2 different paths, one that sort of bends down and is going to have a negative line integral, and one that sort of bends up and has a positive line integral. Okay, for the most part, if you have a vector field that does not have path-independent line integrals, and you want to convince yourself that they're not path independent, you could just pick 2 points and pick 2 paths. Usually you're just going to get random junk and therefore unequal junk if it doesn't have path independent line integrals. So I'm just going to pick, for example, maybe this parabolic path. This one's going to be sort of bending up above the line y equals x. And then this x2, this is going to be another parabolic path, but it's going to be bending down below the line y equals x. Okay, and both of them just t going from 0 to 1, so that they start at 0, 0 and end at 1, 1. And then we'll compute the integral along the curves traced out by these paths. Okay, so for the first one, C1 traced out by x1 here. What's the vector line integral? Well, okay, again, we plug this into the vector field. So t squared is my x, t is my y. I get this. This is my velocity vector, right? Take the derivative of both of those entry-wise, then dot them together. I just get the integral of t squared from 0 to 1. That's a third. Okay, so the first vector line integral along that parabolic thing going above the line y equals x, that's a third. Okay, if I do the parabolic arc going below the line y equals x, then, okay, now this is the path x2, tracing out this curve c2, okay, and just some stuff flips around. This time x is t, so I get negative t in the second entry. Y is t squared, so I get t squared in the first entry. Velocity vector, dot them together, compute that integral, you're going to get negative a third. And, well, yeah, wouldn't you know it, those are two different values, right? The vector line integral, one way was a third, the other way was negative a third. Even though they're starting and ending at the same points, the curve in between, the route that you took to get from one to the other, mattered. So this vector field does not have path-independent line integrals, okay? All right, let's go back a little bit. Let's go back to that first example that we saw in this video, right? This vector field xy squared, x squared y. Okay, we did one particular example on it to try to convince you that there's something neat going on. Let's really actually show that it has path-independent line integrals now, okay? So let's really show that this is true, not just for those two particular paths between 0, 0, and 1, 1, but, you know, if I pick any two endpoints and any two curves going between them, yeah, I'm always going to get the same answer. Okay, so let's show this. And the trick is going to be, well, let's use Green's theorem from last week. Okay, what I'm going to do is I'm going to say, okay, suppose I've got two endpoints, A and B. Okay, and now I've got two curves going between them. So C1 goes one way, C2 goes just some other way. What I'm going to do is I'm going to define a closed loop around a region. So what I'm going to call C here is just going to be C1, one of the curves, unioned with what I call negative C2. And what I mean by negative C2 is the curve C2 just oriented the other way, so that it's not going from A to B, it's going backwards from B back to A. So that, like, when I union these two together, I get a curve that's, you know, it's a closed loop. It's going from A to some other point B, but then back to where it started. Okay, fine. Now I can apply Green's theorem, right? I've got a curve going around a region, and Green's theorem then tells me, okay, the vector line integral, it equals the double integral of the region over the region of del f2 del x minus del f1 by del y. And maybe I should clarify a little bit here. Here I've got the curve going clockwise around the region. Okay, really if I did it that way, then I should have an extra minus sign in front of this thing. It's not going to matter because I'm going to show in a second that this thing on the inside here is going to be 0 anyway. Okay, so anyway. All right. In this particular case, what is del f2 by del x and del f1 by del y? Well, I go back up to my vector field, and I take the x partial derivative of f2, that's my second component of my vector field f, and I just get 2xy, okay? And then I do the y partial derivative of f1, and that's also 2xy. Okay, so when I plug that in here, now I just get the double integral of 2xy minus 2xy. Oh, that's the double integral of 0. Wouldn't you know it, that's 0, okay? So this vector line integral around the boundary is 0, but this vector line integral over C, I can break that up into a sum of two different vector line integrals, right? I can break that up because C is the union of these two curves, right? If I integrate all the way along this curve, that's the same as integrating along C1 and then also integrating along negative C2. Okay, so that's what I've got here. And this minus sign rather than a plus sign is just because C2 is oriented backwards. Okay, so I get that this difference of vector line integrals equals 0. In other words, this vector line integral over C1 has to equal this vector line integral over C2. And it didn't matter what the points A and B were. It didn't matter what the curves were. All that mattered is that it was two curves going between the same points. Okay, there are some wrinkles here that I've glossed over. Like here, I drew my curves C1 and C2 not intersecting at all, for example, except at the endpoints, right? But there's no reason that actually has to be the case. My curve C2, maybe it could have done something like that. Okay, in that case, there are some extra technicalities that you got to deal with. This sort of argument doesn't quite work. Even worse, if my C2 did something like this, where for part of the time, it's exactly the same as C1. Okay, there are technicalities there, but for the most part, this sort of argument using Green's theorem works. Okay, now, great. So for this particular vector field, great. Yeah, okay, it's got path-independent line integrals. But like, sort of what was the thing that made this happen? Like, how can I generalize this to other vector fields? And the thing that made this happen was, okay, this quantity equaled 0, so that I got 0 on the right-hand side of Green's theorem here. So when do I get 0 for this quantity? And where that comes from is the fact that, the particular vector field I'm working with here, actually, it's a gradient field, okay? It's the gradient of this scalar field right here, okay, right? If I do the x partial derivative of this thing here, I get x times y squared. And if I scroll back up to my vector field, oh yeah, x times y squared, that's the x partial derivative. And the y partial derivative is x squared y, okay? So yeah, so it's a gradient field from this scalar field, and whenever you have that, you're gonna get this quantity equaling 0, okay? Because, I mean, sort of it's a quick, like, one-line argument, okay? If my vector field is the gradient of some scalar field, okay, then what happens when I compute the x partial of f2 and subtract off the y partial of f1? Well, what I'm gonna get is the x partial of the y partial minus the y partial of the x partial, which, I mean, there was a theorem from multivariable calculus that told us mixed second partial derivatives are equal to each other, so this difference is 0. As long as, you need some mild, nice conditions for that to be true. You need these second mixed partial derivatives to be continuous functions, then you're going to have this equality here, okay? So that's going to be sort of our starting point in the next video, okay? We're going to turn this into a theorem and say that, yeah, this happens in general, okay? Which vector fields have path-independent line integrals? Well, it's gradient fields, even if your dimension isn't 2 anymore, okay? This particular argument only works for dimension 2 because we need Green's theorem, which only works in dimension 2, okay? But we're going to see that even in dimension 3 or 4 or 95, whatever, same conclusion is true. Your vector field is going to have path independent line integrals if and only if it's a gradient field. So we'll start off next class with that. I'll see you then, everyone.